I am the Technical Services Manager for Riello UPS Limited. We all know the DC industry basically has become one of the fastest growing and transforming industries of the last decade. Now we've seen transformations in terms of ecosystems, technical and regional requirements, system architecture, power demands, efficiency, and of course, total cost of ownership. Now, as a result of these transformations, the data center has obviously come under the spotlight, having become very power hungry and obviously costly to operate. Now, in addition to this, with obviously 150 plus countries signing off the COP agreement by 2020, aiming to reduce the global temperature by 2 degrees, with a strong CO2 reduction targets set down for 2030 per country. Basically, sustainability has become one of the main challenges for humanity. Now, fortunately, in addition to this, we have growing inflation, we have geopolitical instability and the related energy crisis along with that. And obviously, we have industry supply chain difficulties. Now, the industry is effectively facing strong headwinds and obviously making the whole business even more challenging. So the question is, from a Riello standpoint, is how can we help the DC industry become more sustainable whilst at the same time minimize operating costs? Well, we can start by looking at power demand and how the very latest high efficiency uninterruptible power supplies can dramatically reduce energy loss, cooling requirements, operating costs, and ultimately the CO2. In addition to this, we can look at the total cost of ownership and how advances in UPS design have helped reduce costs by using high quality, long life components, provide user flexibility, and of course, reduce the overall maintenance costs. So let's take a look at power demand and high efficiency double conversion UPS systems. Well, basically, the measure of any UPS's efficiency is defined as the kilowatt input versus the kilowatt output. Now, the difference between the input and the output power is effectively lost energy, which is technically completely wasted. Now, this wasted energy is mostly converted to heat, which generally needs to be either removed and or be cooled, which again requires more energy. Now, basically, the greater the energy loss, the lower the efficiency, the higher the costs, obviously. Now, every UPS manufacturer obviously ultimately strives to produce a UPS system that could achieve a 100% efficiency. However, like I say, sadly, however, due to current technology and of course the laws of physics, this is simply not possible at the moment. Now, however, through advanced UPS design and the very latest in component technology, we can get very close. Now, before we start actually looking at that technology, I just want to explain to you a little bit about online dual conversion UPS systems and how they operate, and the 3 typical modes that they will be used in a data center application. So on the screen there, you can see that's a typical diagram of an online dual conversion UPS system. On the left, you have the input supply. On the right there, you have the load. At the bottom, you have the batteries, which are obviously there to support the UPS system when the main supply fails. And at the top, you have the bypass line, which is obviously used for things like maintenance, for issues, alarms, faults, and so on. Now, the online dual conversion UPS system is so called because basically we take the supply from the incoming main supply, the AC, and we convert that to DC. So that's our first conversion. Then we take that DC and we reinvert that back to AC again. That's referred to as our second conversion, hence the term dual conversion. Now, the beauty of the online dual conversion UPS system is effectively the inverter is running permanently online. So the inverter is permanently providing us with the clean AC waveform for the critical load, regardless of what is coming into the UPS system from the main supply. So based on this, we can say that the online UPS system provides the very highest levels of protection against any network disturbances, in addition to the maximum power conditioning. The downside of the online dual conversion UPS system is because of the conversions which are taking place within the UPS, unfortunately, it provides the lowest level of efficiency in terms of the operating modes of the UPS system, and so the UPS system is obviously has losses. Another mode of operation for the online dual conversion UPS system is the eco mode. Now, the eco mode is exactly the same UPS. They can all do these features. The eco mode is basically operating whereby the load is actually now being powered through the bypass line. So this time the UPS system is not performing the dual conversion process, albeit we are still maintaining the batteries so that in the event that there is a mains failure, the battery system will be available should it need to be. Now, one of the benefits of the eco mode of operation is that it's obviously provides the very highest levels of efficiency, somewhere near 99+%. However, because the input is effectively connected directly to the output, there is little to no protection against instant network disturbances, and therefore it provides the lowest form of protection for the critical load. So what you gain in efficiency, you lose in the levels of protection. In addition to this, most systems, in the event of a main supply failure, there would be a small break in the supply to the critical load. We're only talking milliseconds when the main supply break occurs, and therefore, obviously, this is not a favored mode of operation by data center managers. The next mode of operation is sort of like a mixture between the eco mode and the online mode. This is referred to in our case as active eco. Some manufacturers will call them dynamic eco, various different names. They'll all give them different names against this thing. But basically, it's very similar to the eco mode in that the load is being provided through the bypass line, so we've got a good high efficiency. However, this time now, the actual UPS system inverter is actually working in parallel with the bypass line. So it's effectively working like an active power factor corrector or a power conditioner in terms of power factor correction, SAGs, THDI, and so on. So what it's doing is actually, if any nastiness that's being produced by the critical load, that's not being reflected onto the grid, whilst at the same time the UPS is actually basically subsidizing that voltage or that quality of waveform. Now, the benefits of this, again, efficiency sits somewhere between the eco mode and the online mode. However, this time, you've got that power conditioning. But the downside, because it's still directly connected, you still have little to no protection against network disturbances. And so, again, it's great to have it, but it's not a favored solution. Now, I can say with certainty that most online UPS systems will provide you the very highest level of protection. Now, nearly all DC managers will typically operate their online UPS systems permanently in online mode in order to minimize any potential risks to the data center. So what I'm saying here is that when comparing UPS efficiency, we must always compare like for like. Otherwise, we cannot establish a true performance of the potential savings that could be gained by, upgrading UPS systems. Now, basically, in my view, is that anything other than true online can be a bit of a gamble in terms of power protection. Now, when stating efficiency, many UPS manufacturers will produce what is referred to as an average efficiency figure, which is effectively a combination of operating modes over a set period of time. So, for example, over a 24-hour period, for 12 hours of the day, the UPS system could be in online mode, and for the remaining 12 hours a day, the system could be sitting in eco mode. Now, obviously, for certain applications, this is perfectly acceptable, but for 24/7 data centers, this is generally not accepted because you are at some point exposing the data centers to higher levels of risk. Unfortunately, because of this, the average efficiency typically is not a true representation of the real life conditions. And so the figure cannot be compared to the true online figure. So basically, the average figure will typically show an inflated efficiency value, which can be a little bit misleading when you're trying to work out a total cost of ownership, i.e. the energy you're going to be saving long term. So what we can say here is that high efficiency UPS systems, on the other hand, can effectively achieve extremely high levels of efficiency, even in online mode. So there is no need to settle for average performance. Now, this is not so much as a sales pitch, but just to show you a typical system that is available in the market. This is a high efficiency modular UPS system that's produced by Riello UPS. It's an online double conversion system, and it will provide a true online efficiency, though, so this is permanently online mode, higher than 98%. Now, the system is the Multi-Power 2. Now, this is based around a flexible, scalable, resilient, and sustainable UPS system. Basically, the main building block of this UPS system is formed around a 67 kilowatt power module. Now, that power module is then matched to 3 specific power cabinets. You have a 500 kilowatt power cabinet for small applications. You've got a 1 and 1.25 megawatt power cabinet for larger installations. And again, you then have a 1.6 megawatt frame for, again, larger installations, and all of which of these cabinets can be put in parallel in order to provide additional resilience to a cabinet level. Now, within all of these cabinets, as I was saying, the module forms the core of the cabinet. So basically, the systems are populated with fully hot swappable power modules to suit the load required at the time. In addition, inside those cabinets, you've got spare slots where you can fit redundant modules, so you can have redundancy levels. In addition to this, the system has a fully rated bypass cabinet. So again, the event has a problem. It has a fully rated bypass system. And also you have within these cabinets is full flexibility in terms of, you can see down the left is a 1 and a 1.1 and a 1.25 megawatt solution with switches. Some people want the input and output switches to suit the installation. And on the right there, you will see that you have the same installation where you have the system without any input switches. So the whole point of this system is it's flexible in terms of its modules. It's scalable in terms of it can be increased and decreased in size accordingly, automatically if you wish to. It's resilient because obviously you've got the redundancy, and it's sustainable because of the technology, which I'll come on to in a second. So again, fully hot swappable modules, fully rated bypass switch, and redundant slots. But in this case, this has a backfeed protection as an option. So again, it's flexible for all kinds of installations. So what I want to do now is actually look at how we actually got to this point in the marketplace. So let's look at where we went in terms of the innovation in terms of UPS design. Well, many years ago, we used to produce UPS systems, was what's referred to as a two-level architecture inverter. So effectively, UPS systems of this type would typically produce an efficiency level of around about 96%. Now, don't get me wrong, that is a very good efficiency even by today's standards, but obviously it's not as advanced as it is as we are now. We then made the step from move away from the two-level architecture across to the three-level architecture. Now, the three-level architecture obviously requires more components and it requires more processing power to which to control. So typically, when these were first introduced, you would only really see three-level architecture systems in place in large UPS systems, 100, 200, 300 kVA plus. Because of obviously the complexity, the number of components, and obviously the overall cost. It was not cost effective to produce UPSs with this architecture. However, nowadays you will see, because of technology has moved on, you will see the three-level architecture in UPSs as small as 10 kVA. The next stage, obviously, just coming back to that took us up to efficiency levels of around about 96.5%. So the next stage then was the filter design. We've changed the materials that are used in our filter designs, which enabled us to push the efficiency of a UPS system up to around about 97%. So we're getting somewhere, we're making progress. Now, the biggest change that we've applied in recent years is the move from traditional silicon components over to silicon carbide. Now, the use of silicon carbide components is nothing new in terms of from a component perspective. It's actually widely used within the electrical car industry. And obviously, because we've seen such an increase in electric cars, this has obviously pushed the technology further and made it more readily available. So hence, we were able to move from traditional silicon IGBTs to MOSFET silicon carbide devices. Now, with these changes, we can now operate the UPS systems in online mode up to 98.1% efficiency. Now, the way we can do that is the table at the top there is basically a small comparison between a traditional IGBT versus a silicon carbide device. And as you can see there, first of all, the total chip area, you can see the chip area is about 20% of that of a typical IGBT. So it's much a smaller component. The conduction losses, you can see actually silicon carbide has slightly higher conduction level losses compared to a traditional IGBT. But where we gain it is in the switching losses. You can see basically that the switching losses are around about 25% of that of a traditional IGBT. So overall, using silicon carbide, we get around about a reduction of around about 50% in terms of the heat generated by the device during operation. And the graph at the bottom there effectively shows you the load levels across the components at 10, 25, 50, and 100% load. And as you can see, the silicon carbide devices constantly outperforms the traditional IGBT device. So it's not as if the device just operates at a certain point or sweet spot. It will basically outperform the IGBT across the load rangings. So what can silicon carbide bring to us? Well, there are several advantages. Because there are less losses, we produce less heat. So that means we have to provide smaller heat sinks. There is excellent thermal management because of this. We have reduced component stress. We have very high power density, and we have smaller components, which equates to a smaller design. Now that particular power module there, again, it's ultra high efficiency, running at 98.1%, and that's been independently verified by Kiwa. Now the benefits again of this is an increase in reliability because of the changes in the components. If we actually look at the performance, this is a typical performance graph of a 500 kilowatt system, which is operating with silicon carbide devices. And as you can see, the system is operating greater than 98% for a load range of around about 25 to 50%. Now, normally that would generally be higher up the load ranging. However, it's slightly different with silicon carbide. We can also see, however, that we are still greater than 97.5% efficiency for between 15 to 80% of the load range. And again, still further, we are greater than 97%, even from 10 to 100% efficiency. So in terms of performance, it's extremely good. Now, one of the main things of this is in online mode only. This is not in eco mode. So what savings could be achieved from this? Well, basically what we can achieve is, because there are reduced heat output, reduced wasted heat, and reduced cooling requirements, obviously our operating costs are going to come down. In addition to this, because we're using long life components, maintenance-free capacitors, and we have a high MTBF, which is effectively mean time between failures, and a low MTTR, which is mean time to repair, we reduce our overall maintenance costs. So again, this power module, obviously, it's very compact. It's high efficient. It's 6 to 7 kilowatts in 3U. It can operate up to 40 degrees C. So again, the operational rooms can be run at high temperatures, less cooling required. It can charge batteries up to a high current. Easy to handle at only 37 kgs. Fully independent, hot swappable, fully isolated from all the other modules. So again, reduced fault propagation. And it has fully firmware and parameter auto alignment. So it's very easy to use, and that's one of the benefits of this system. Now, it's not just the efficiency that we've looked at. We obviously have to look at the sustainability of the modules, and obviously the way we construct them. And so what's happened here is we provided a much cleaner, simplified design layout of the actual module itself. We provided special humidity and temperature sensing. We have put input air temperature sensing. We have added capacitor temperature monitoring. We have added PFC and inverter temperature sensors per phase. Now, one of the benefits of this is it gives us a full thermal map for monitoring and predictive maintenance. So again, we can plan exactly how the module is going to perform over its lifespan. In addition to this, because of the advanced design, its manufacturing is quick and simple. It's fully recyclable. You've got reduced weight and heatsink volumes. We've got very granular monitoring, quick and easy assembly. It's very high reliable, fully recyclable, and the long life components and the very short mean time to repair. Now, if we look at that in terms of costs, in terms of maintenance, because we're using long life components, now no capacitor replacements needed to be performed over the full lifespan of the system. Now, when we define lifespan, we say 15 years. Now, typically, a UPS system in operation would require capacitors, fans, etc. changed, typically anywhere between 5 to 7 years. So, and obviously that's got a significant cost. It's got a reduction in resilience and so on whilst that work is being performed. In this system, we operate long life components, so there is no need to change the capacitors for the full lifespan of the product. In terms of maintenance, the only worst case is actually the system will only require a single fan replacement in its lifetime. Now, when I say a single fan, I don't mean a single one fan. I mean all of the fans change once. Now, the benefits of this is again, it's going to reduce the maintenance. Worst case scenario would be this would have to be changed halfway through the life of the product. However, depending on the operating conditions, load levels, etc., it could mean that the fan replacement can be completely avoided. So again, for the full 15 years, there's absolutely no maintenance required of the modules. Obviously, if it's a dusty environment, obviously it would need to be cleaned. The controllers carefully monitor all consumable components, so we can provide a fully comprehensive self-diagnosing and aging system. In addition to this, there's obviously intelligent and advanced thermal monitoring. So what does this affect, and how does this affect the total cost of ownership of our UPS systems? Well, basically, the way this works is that if we look at down the total cost of ownership on the graph there, you can see the greatest portion of energy costs and the next greatest portion is operations and maintenance. So we've focused primarily on these two areas. If we deploy a UPS system, put a 98% UPS in replace of a 95% UPS, don't get me wrong, that is a well-performing UPS system. And based on a 1.25 megawatt UPS with a 1 megawatt load, you can see pence per kilowatt, 15 pence, cooling coefficient 2.5, CO2 0.2 kgs, climate control levy of 0.77. I have not included for reactive power, maintenance costs, annual decrease in CO2, or any annual increase in electricity costs. So if we look at that, by deploying a 98% efficient UPS versus a 95, we could make savings of over 400,000 kilowatt hours per year. This equates, based on 15 pence, £63,000 per year saved. Over 15 years, that's nearly £1 million. Over a year, we would save 82 tons of CO2, and over 15 years, over 1,230 tons of CO2. So as you can see there, it's not just about the power. If we, based on component cost alone, because of the maintenance, a typical site could save in excess of 80 to 120,000 pounds over a 15-year period. And because of the advanced diagnostics, it significantly reduces engineers' time on site, thus reducing costs through resource requirements. True hot swappability makes it easy to use and quick to repair, and a low mean time to repair, less than 30 minutes, means maintenance and contract prices can be kept low. So just summing it up, always compare like for like, always make sure that you're comparing an online UPS system with an online UPS system, not an average figure. It's very favorable CapEx. Typical a module is probably anywhere between 7 to 12% difference in comparative to a standard module. So again, it's not a big difference in cost. Very high power density, potentially no overhaul component cost, low mean time to repair and maintenance costs, significant CO2 savings, reduced cooling requirements, basically by installing a high efficiency UPS in place of a legacy UPS. Even at 95% efficiency, we're replacing UPS in the field of up to low as 88% at the moment. A typical installation of 1 megawatt could provide a saving of over £1 million over a 15-year period. So it's obviously significantly worth, and the payback is obviously significantly quicker than it would be to a lower efficient UPS system. So that is the multi-power high efficiency UPS, designed and manufactured obviously by Riello UPS in Italy. I'd like to thank you for listening to my presentation. I hope you have found that interesting, and I would like to take any questions that you may have. Go for it.
It's always a one you probably hear all the time, but obviously one of the large costs with buying a UPS is the initial outlay.
Correct, yes.
So how can companies reduce that upfront cost? Is it ensuring they spec the system for the future, or by right-sizing it now?
Yeah, I mean, this is the one thing we always do see. We always revisit data centers that have been, installed many years ago, and we, many times we see them completely underutilized, and it's a shame because what they plan to install from day one has never really hit that targets. The beauty of these systems, yes, quite rightly, yes, the capex at the beginning can be significantly high. The beauty of the OPEX is obviously that you're going to get that payback much sooner along the operational curve. And obviously, with a scalable solution, especially in this case, some people will install them in terms of they will utilize a fully automatic system whereby they will fully populate with all of the hardware. And then basically what they will do is, as their load on their data center increases, decreases, or changes, the system will automatically bring online the number of modules required in order to fulfill the requirement to maintain that redundancy level. So some people either do it that way, or some people aim to, well, we're just going to populate, we're going to put the cabinets in place, and we will just populate with cabinets as we see fit. So there's different ways of doing it, but the main thing is obviously in terms of the costs, obviously, like I say, when you're looking at a system of this type, well, I put in a silicon carbide module, it's only the module that differs, the cabinet is the same. So, it depends on the size of the system, but, the difference in cost is going to be somewhere between, 7 to 12% difference in cost, which is not, when you look at the big numbers, is not a huge amount. So it's very well worth it employing it. So people will look at it differently the way they install it, to be honest with you. If they want to, if they've got the capex, they will put it all in place day one. Hopefully they're going to use it. So put the pressure on the salesman to sell the space.
Yeah, you want them to obviously buy as much as they can
Of
afford
course,
and
yes,
need,
yes.
but
And buy a spare
obviously.
one as well.
Michael Cunningham asks, on the subject of paybacks, do you have
Yes.
any example of paybacks that have been achieved through installation of the high efficiency systems?
Yes, we did one recently where the actual system was in operation and it paid for itself. From the hardware perspective now, it just paid in, I think it was just before year six, which was very good. Obviously, you've got to then consider payback in terms of batteries and things like this, but purely from a hardware perspective. But what we try to do in situations like that is try to get more real life, because there's so many variables in terms of payback, because obviously you've got the cost of electricity, so many people are paying so many different values these days, and you've got everything else that goes along with that in terms of climate control levies, you've got reactive power charges, all these additional bits. We always try to do is a case of, I'd prefer to be presented with this is what I've got, how much could I and how quickly could I pay that back, and have more of a real time. But yeah, the one we did recently was, I think, just around year six,
It's not
remember
bad at
rightly.
all,
It's not too bad
really.
at all. No, it's nothing to be sneezed at, that one, no.
No. And someone, Charles Galtrey asks, you say that the efficiency is verified, but who carries this out for the UPS sector? Who
So
verifies them?
it depends. There are different, obviously you can go for the likes of TUV would do certification for you. We had this one independently verified by Kiwa. And in actual fact, that was the module, I believe, if I remember rightly, was operating at an output of 230 volts. If we actually operate those modules at 240 volts output, I believe we actually achieved a 98.3%, but that's not been independently verified. We've only gone by what has been independently verified, and that was done by Kiwa.
Okay, perfect.
Yeah.
If anyone else has any other questions, by all means, you've still got time. I've got one more question.
Certainly.
Which is another way that you could reduce the total cost of ownership of any UPS is through maintenance.
Yes.
What are the top tips that you would share to ensure you get longevity out of a modern UPS system?
I think the key one is stick to the manufacturer's guidance in terms of maintenance. It's very important, because it can become very costly if it goes wrong.
Yeah.
Obviously, components within any UPS system, like any components that we use, have a finite lifespan. For the likes of capacitors, fans, etc. Obviously, there are variables that will change this in terms of load levels and so on. But I would always suggest that people follow the guidance, and you push them to their limits, and you go into a bit of a no man's land where you're risking, you're balancing basically your resilience to your data center against costs.
Yeah.
And there comes a point where and you get to a point where you're not only balancing in terms of resilience and cost, you also balance in terms of danger, where you are taking components way beyond their design life. And Paris thought, the worst case scenario, a component fails, it's dried out, it ignites, you have a fire. Worst case scenario. So again, I think for me, it's all about follow the guidance. Those that we don't set that to make money out of it, because otherwise we would never have developed this new product where it's maintenance free, because that's not what we're trying to achieve. We're trying to achieve sustainability, and TCO. That's what we know. That's our remit that we're trying to focus on. So.
And that is so important to many companies
Correct,
these days. I think every company has a big concentration on TCO,
yes.
especially,
Yes.
but also these days sustainability and obviously net zero is a huge thing.
Yes.
Once again, a massive thank you, Jason,
No
for
problem.
joining us
My pleasure.
again for Powered On Live 2023. Maybe we'll see you again in
You certainly
2024.
will.